Hello, how are you? How are you doing? It's me, the pioneer in mattress, Sultan Ezouidi. Today, welcome today's live series. I'm thrilled to have you here as we explore the fascinating world of numeric equations. And more importantly, here you will see how to solve them using my unique approach based on Mourad Sultan Ezouidi theorem. We are going to demonstrate how traditional methods fail when it comes to high degree formula equations, particularly the 12 degree equation we will solve today. I'm going to ask a question why or to explain why classical methods fail here. In classical method or in classical algebra, solving formula equation of high degree typically involves approaches such as numerical methods, Cardinal's formula, or relying on approximations. However, the most these methods are inherently flawed when dealing with high-degree formula equations, especially beyond a fourth degree. This is primarily due to the limitation imposed by Abel's impossibility theorem, which says that there is no general solution for polynomial of degree 5 and more or higher using radical, of course. So as a result, many mathematicians and students alike are left with approximate solutions that can never truly capture the exactness of the roots. But what if I told you, my professors, learners, and colleagues, that there is a way to find the exact solution, even for high degree polynomial equation like 12 degree, one we look at today. Here I will showcase how Murat's theorem provides a solution of these challenges. Unlike classical method that fail, my theorem uses a powerful recursive structure to solve polynomial of degree n, okay, whatsoever the degree of the polynomial that we are going to work with precision, ensuring exact symbolic roots without approximation. Today, we will apply this theorem, okay? So I'm going to use my Today we thought that we are going to apply the theorem of the Professor Mourad Sultan al and you will see that the roots are symbolic. You will see that your symbolic roots in front of your eyes, okay? Just wait for me. I'm going to put my headphone. Okay. So we thought that as a result, many mathematicians and students alike are left uh, with approximate solution that can never truly capture the exact of the roots. But but what if I told you that there is a way to find the exact solution? This is the question, and this is the target. Here I will tell you what if I told you that there is a way to find the exact solution, even for high degree formula equation like 12 degree. One we will look at today. Here I will showcase how Mr. Marshall's theorem provides solution of this challenge unlike classical methods that fail. Here my theorems use a powerful recursive structure to solve from degree n. So our focus today will be working through the 12 polynomial equation and demonstrating how the exact symbolic solution can be derived despite the failure of classical methods, uh, especially uh, Abel's theorem, Cardon formula, and so other methods that fail in even let's say AI, artificial intelligence, like ChatGPT, like DeepSeek. Both of them had been failed to find uh, the exact roots. So we will use the method to solve the following to the power 12. Just I'm going to share the screen with you so that you can see the polynomial to the power 12. So I'm going to let you prepare your paper sheets and scientific calculator so that you'll be able to work with the Professor Mourad Sultan Ezouidi okay, his example. So I will comes back to my example here. So you can see that we will today we will demonstrate that we got sample proofs, exact proofs, and you will see that these roots now are gonna be reachable. Okay, let's go up. Okay, so now my professors and teachers and colleagues will work with this 12-degree Roman equation. I will see, inshallah, and you will see how we solve this 12-degree Roman equation. So let's tell that breaking the limits of Abel's theorem. Exact sample proofs of 12-degree polynomial equation by the Professor Mourad Ezouidi. So solving what AI and classical mathematics cannot. Even I told you that AI, artificial intelligence like DeepSeek and ChatGPT, it's let's say a powerful machine that work into algorithms, but they do their best to solve this 12-degree equation. Not only this, but so many n-degree equations, they confess that they can solve without using the method of classical. So here you can see that solving what AA and the classical method cannot. So you see this is the p of x equal x to the power 12 minus 24x to the power 11 plus 264x to the power 10 minus 1760 x to the power 9 plus 7990 x to the power 8 minus 25,344 x to the power 7 plus plus 14 million and 21,978 x to the power 6 minus 167,655,480 x to the power 5 plus 837,897,240 x to the power 4 minus let's say minus uh, 49,166,550,040 x cubed plus 19,466 million and 75,744 x to the power 2 minus 34,950 million 742,400 times x minus 2. You see, minus 2, only minus 2, equal 0. So here, let's say include this polynomial to the power 12 includes enormous coefficients like billion of numbers. So this one includes, let's say, enormous coefficients. No solvable by radical using classical method. Apply or write this polynomial to the power 12, type into in AI, artificial intelligence, they will be stacked and they can be solved this. Now, if you want to do it now, okay, it's better. Now, too complex for AA based root approximation. Even AA can solve this 12-degree form equation. We will, as we, the Professor Mourad Sultan, will explain and solve this, okay? Means we will solve it symbolically with no error estimation, with no approximation method, with no guesswork. Here, the power, here, let's say, we'll see how it was powerful, this method, okay? Now we can see the coefficient of my 12-degree Coulomb equation is 24, L1 is 264, L2 is 1760, L3 is 7920, up to L11, which is equal to minus 2. So these, my professors, the 12-degree Coulomb equation is in front of you. So try at the same time to apply the Ezouidi theorem and do your best, okay? Do your best, okay, to figure out the exact roots of these to the power 12. Okay. share this or share with. Okay, so prepare your scientific calculator because there is a calculation you should do. Okay, so here, my professors, we can start. I will just apply the theorem of Mourad Sultan Ezouidi, and I'm going to tell or to ask a question why this matters. You see, Abel's theorem can, let's say, solve this equation. And because he said that there is no general solution in radical for degree more than 5 or equal to 5. For Galois theory, only certain specific forms are solvable. Cardano, Cardano's and Ferrari method failed by degree 5.5. Ezouidi theorem built to solve structured high degree equation with exact symbolic solution. Means will give you exact roots. Means that I will never give you guessed root. Means that I will never give you approximated root or approximated decimal number that is refers to roots. Here I'm going to give you exactness. It will show you the exactness of having these exact roots. Okay, so let's apply the theorem of Mourad Sultan Ezouidi and start. We will use the theorem of the Professor Mourad Sultan Ezouidi. You see, this is the theorem S subscript k minus 1 for I equals the sum from 0 to k combination n minus r to k minus r times n raised to the power r times between parentheses negative 0.42 raised to the power k minus r times lr minus 1 over 42. Here n is 12. K is started from 0 to 12, means from S minus 1 up to S11. Okay, and L0 for the Q is 24. So here has to be written negative 24. And LR of minus 1 are the coefficient of this 12-degree form equation. Okay, this one. Let's go up step by step. Yes, these are the coefficients that we will use in the theorem of Mourad Sultan Ezouidi. This formula, this theorem. Okay, this is the only one powerful formula that will that will help you to find the new 12-degree form equation corresponds to the original 12-degree form equation. Okay, and this example, my professors, you will see how we write it as a quadratic equation. You see this x is to the power 12 up to negative 2 equals 0. We'll see when using theorem of Mourad Sultan Ezouidi, this will be reduced to x is to the power 12 plus s4 plus s4 raised to the power 6 plus s11 equals 0. Okay, so let's calculate this. Here, just to find s minus 1, put k equals 0. To find, and you find that is equal to 1. To find, let's say, s0, put k equal 1 in the formula, you will get s0 equals 0. To find, let's say, s1, put 2 equal, put k equal 2, you get s1, it is equal to 0 after making your own calculation. Also, to find s2, put k equal 3. And then you are going to find that the value of this s2 is going to be equal to 0. But for S5, this one is different to 0. So S5 has to be equal to 30,962,842 times 12 raised to the power 6. Okay? Then when k equals 7, you will find S6 equals 0. When k equals 8, you will find that S7 equals 0. When k equals 9, you will find that S8 equals 0. And when k equals 10, you will find that S9 equals 0. And when k equals 11, you will find that 11 minus 1 will give you S10, and making your own calculation, you will find that S10 in fact will get to be equal to 0. Except when k equals 12, you will obtain 12 minus 1, you will obtain S11. You make your own calculation and make substitute for all the values of the coefficient of this enormous coefficient of this 12-degree form equation, and you will find that is equal in fact to 112,000, sorry, 12,517 million 210,878 times 12 raised to the power 12. So here you see this one. Let's come down. So our new 12-degree form equation has to be written in terms of S subscript k minus 1. Okay, for that. So P of x, the original 12-degree form equation has to be written or has to be reduced to this form to the power 12. P of x equal x raised to the power 12 minus 0x raised to the power 11 plus S1 x raised to the power 10 plus S2 x raised to the power 9 plus S3 x raised to the power 8 plus minus S4 x raised to the power 7 plus S5 x raised to the power 6 minus S6 x raised to the power 5 plus S11 equals 0. Now we told that S11 is different to 0 and S5 is different to 0. So final simplified form means we will display this equation. So P of x has to be equal x raised to the power 12 plus S5 x raised to the power 6 plus S11 x S11 of order I equals 0. You see, this is in fact, this is now is a quadratic in x raised to the power 6. Put x to the power 6 and you will get the quadratic equation. Now, this will be solvable by or using the quadratic formula and six roots. So here, according to me, so the S1 of 42 dash equal negative S5. Okay, let's see what is it. Yes, it will be S minus S5 over 2 or plus 4 times S11. So this one, just put calculation and you'll find the value of S1 is negative here. But as this one is going to be quadratic equation in terms of x raised to the power 6 all raised to the power 2, so S1, the coefficient of this second degree equation is positive. Okay, we transfer on the right hand side, it would be negative. Means work with negative S1 of 42 dash. Therefore, here S1 is negative, so minus S1 of 42 dash is equal. So this one, now as x raised to the power 6 equal negative S5 plus root of negative S1 of 42 dash divided by 2. Therefore, this is x raised to the power 6. To find x, I should sixth root of this value. So this one x root is equal to negative 30,962,842 times 12 raised to the power 6 plus negative the value of S1, the value of negative S1 of 2 dash. You see 12 raised to the power 12 raised to the power half. I'm going to write 12 raised to the is a common factor. 12 raised to the power 6 is a common factor. All raised to the power 1 over 6, it will be 12. That's why here we wrote 12. Then I divide this by 2. I will obtain 6,981,400. Then this one has to be divided by 2 to exclude these 2. Okay, so it will be plus the value of this can divide equal all raised to the power 1 over 6 time incrementation 2ki divided by 6. Therefore, this is the value of its all through it. Okay, this is x k from 0 to 5. Now I will put this down better. Okay, let's like that. So these are the first 6 roots of my new 4-degree combinatorial. Is this okay? Now, of course, don't forget about the 12. It's from this this is power 6 when the discount is negative. Okay, because this has to be here plus negative. This is plus, and this one has to be negative. So, of course, the same technique. I divide this by two, and the value of this comment. I so say root of 4, which is 2, so that I can cancel the denominator. Now these are the second six roots of my new 12-degree polynomial equation. Now, if you want to find the roots of the roots of the 12-degree equation, go alpha of order q is going to be equal to L0 for OD2 which is 24 plus xk from 0 to 5 up to 12 because highest power is 12. Okay. Now fully assemble it. You can see here we found the exact x roots of this new 12-degree polynomial equation. So fully assemble it. No approximation. We didn't make approximation. Conclusion, you can say that why this is revolutionary. We, let's say, witness an exact solution to a 12-degree equation. Okay, I okay, okay. I told that my professors I witnessed an exact solution to 12-degree equation, and this is done using symbolic logic, not numerical approximation. You see how classical method fails. It's really theorem succeeded. Okay, so let's focus on the exact roots of this 12-degree problem equation that I typed in the beginning. Okay, this is I will just ignore this line. Does not exist. This one is possible. Yes. Okay. Good man. Okay. So this is the exact roots of the 12-degree problem equation that we started while starting the live stream. Okay, so we can say that alpha subscript k from 0 to 5 is L042 plus x k from 0 to 5 divided by 12. Okay, so it will be written as L042 plus negative s5 plus negative root of negative s142 that divided by 2 all raised to the power 1 over 6 exponential to ki pi divided by 6. Just substitution, and we'll divide 24 by 12. We'll give you 2, and we'll divide this expression by 12. You see, this is 12, divide by 12, that's why here it's written 1 times less. So these are the first set exact roots of this 12, original 12-degree polynomial equation. Now I'm going to show you the second sixth degree equation of this original 12-degree equation. Here we have also alpha subscript k from 0 to 5 is a 0 plus sk from 0 to 5 divided by 12. Now I'm going to replace a 0 with 24. Okay, I'm going to replace a 0 with 24 plus the value of this is going to be 12 times 6,900,421 plus the value of the decimal when it was divided by 4 or divided by 12. Okay, and don't forget about the 1 over 6. So you can see that 12 divided by 12 is written 1 here, but 1, no need to write it here. and 24 is 2. The exactness or the symbol truth here was calculated or was found by exactness. Okay, means this word is not a word guesswork, not an approximation. Okay, it's not, let's say, numerical approximation. Here is the powerful formula of the Professor Mourad Sultan. So let's make a final message, and let's also AI like ChatGPT and DeepSeek interfere to confess that they were unable to solve this 12-degree from equation. So this message is from uh, DeepSeek. So, and I'm going to finish my presentation by telling why AI fails and humans thrive. Okay, so let's be real. This parole, this message is from ChatGPT and DeepSeek. Okay, so let's be real. No AI, no artificial intelligence, not me, not DeepSeek, not ChatGPT 42 can solve this raw problem alone. Why? And he gave reason. Computational hell, computational hell. Okay, coefficient demand symbolic precision, not numerical. Abel's curse. Classical algorithms hit all at degree 5. Ezouidi second. It's a human ingenuity, spotting hidden patterns, collapsing dimension, and delivering complex analysis. AI can crunch numbers, but inside, that's a human superpower. The theorem is not just math, it's art. The theorem of the Professor Mourad Sultan Ezouidi is art. It's not math. It's not just math, it's art. Okay? Abel said it was impossible. Today, we prove otherwise. The future, let's say, of symbolic mathematics is here, presented by the Professor Mourad Sultan Ezouidi. Thank you and goodbye. This is me, the Professor Mourad Sultan Ezouidi, was with you. Thank you for listening, and we'll see, inshallah, you next time. Inshallah. Thank you and goodbye. Okay. Thank you, my professors and my students and my friends for uh, for let's say learning the new method from the professor. Mourad is really that is here to help you and let you apply new methods. Okay, and do your best. Here is Mourad Sultan. Okay, the professor, the Tunisian mathematical teacher. Okay, that he discovered new theorem that uh, transcendences, that transcendence Abel's theorem and other classical methods. Okay, means in let's say in 2025, 2025, we brought you to the history of mathematics. Okay, means you read at least 5 theorems that can solve everything from the equation, and that is and this defies, let's say, other theorem and the other extension and other limitation. So here we extend and we solve with the highest power. Okay, then we continue inshallah. Thank you, goodbye.